nearing the end of the new material in chapter 12, and we've been in psychrometric, so a study of moist air. And what I'd like to do is start with a problem, this here problem. So that we have moist air at 48 degrees C, 101 kPa, 30% relative humidity, and it flows across a heat exchanger where it is cooled and comes out at 15 degrees C and 101.3 kPa. And then determine the exiting relative humidity, amount of liquid condensate per kilogram of dry air, and heat transfer during the cooling process. So make a little sketch like this. Here's our duct. Here's our cooling coil that's in the duct. Air flows over. It comes in and goes out. State 1 for in, state 2 for out. And we'll have a little collection system for m dot liquid. So you'll have flowing in, you'll have m dot dry air as well as the mass flow rate of vapor coming in, and you'll have the mass flow rate of dry air flowing out at 2, the mass flow rate of vapor flowing out at 2. Okay, so we can put more information on the diagram. The dry bulb temperature coming in is 48 degrees C, and relative humidity coming in is 30% relative humidity, and the dry bulb temperature going out is 15 degrees C. All of it's at atmospheric pressure, so we're not changing the pressure. So the first thing is if you get liquid condensation out, that means it's gotten to the dew point temperature and then below the dew point temperature. So you've taken some moisture out of the air, and so the answer to the first question you'll have to check, but if it's coming out here, it's probably coming out saturated air. And if it's saturated air, we expect that the relative humidity would be 100%. So, but we have to calculate that. We have to check it. And so what we'll do is go ahead and write a balance. Let's do there's 3 balances, 2 mass balances, a mass balance. One is really trivial, it's for the dry air. The other one, a mass balance for the water. And then the other is an energy balance. So we do all of the balances for control volume like this. So we have inlet 1, outlet 2, and possibly outlet of the mass flow for the liquid. And then for heat transfer, for the energy balance, you could put it like this. I'll go ahead and put it like this. Some Q dot, not in, but Q dot removed, because it's a cooling coil. It's taking heat out of that airstream. So let's take a look at the energy balance, the first one for the dry air. It's really simple. The mass flow rate of dry air flowing in at 1 is equal to the mass flow rate of dry air flowing out at 2. Even though there's some water possibly condensing, the dry air flow rate's the same, and so we typically get rid of the subscripts and you just have that's equal to a constant. It's just a constant. And now for the mass balance for the water. It's coming in, mass flow rate of the vapor coming in, and the way we'll write it is we'll say the dry air coming in times the humidity ratio coming in. That's one of the reasons we like that humidity ratio. It makes our mass balance for water really easy. So this is how many kilograms of water in the vapor form coming in. That then is the mass flow rate of dry air going out, humidity ratio going out, and if we have any liquid going out. So there's our mass balance for the water. Let's go ahead and rewrite that. So we'll write it this way. We'll write it that the mass flow rate of liquid condensate leaving divided by the mass flow rate of dry air flowing through the system is equal to omega 1 minus omega 2. So if omega 1 is greater than omega 2, then you had some condensate form. And so we calculate now our omegas. I'm going to move this energy balance to this other side, just move it out of the way for now. And let's continue here. So how do I calculate omega 1? Well, you have 0.622 times the partial pressure of the vapor at 1 divided by the total pressure minus the partial pressure of the vapor at 1. So we need the partial pressure of the vapor at 1. And so we go and we look up the saturation pressure at 1, which is the saturation pressure at 48 degrees C. And the saturation pressure is around 10.6 kPa. And then that's from the tables. And then the actual vapor pressure at 1 is the relative humidity at 1 times the saturation pressure at 1. The relative humidity was 30%. So our partial pressure of water vapor is like 3.19 kPa. Well, knowing that, then we can compute omega 1. So we go back to this equation. We calculate omega 1. So that's humidity ratio coming in, 0.020 to, I'm going to give you too many digits, but there you go. So that's how many kilograms of water vapor per kilogram of dry air flowing in. If you assume that it's 15 degrees C saturated air, then P sat at 15 degrees C, you look up in the table, and that's equal to 1.71 kPa. And if you assume Phi2 is 100%, then you calculate omega 2, humidity ratio at 2, and it's 0.010653. And notice that that is less than omega 1, just comparing omega 2 with omega 1. So it's less, hence there was some condensate formed, and we can now calculate right down here that the mass flow rate of the liquid divided by the mass flow rate of the dry air is a difference between those two, and that's equal to 0.009556. So the exiting relative humidity we do confirm is 100% at saturated air, and the amount of liquid condensate per kilogram of dry air, the answer to part B is right here. Now for part C, we need to do that energy balance. I don't know if I left enough room. Hopefully I did. We'll try and squeeze it in over here. And so for the energy balance, we have what's coming in with the mass flow, m dot of the dry air coming in times the enthalpy of the dry air coming in. And then we have the mass flow rate of the vapor coming in times the enthalpy of the vapor, and I'm going to put H of G coming in for the enthalpy of the vapor coming in. So those two contributions, the dry air contribution and the vapor contribution of coming in with those two mass flow rates. Okay. Then we're going to have outs. Well, Q dot is an out, the way we've modeled it. We also have mass flow rate of the liquid times some enthalpy of the liquid, and I'm going to put enthalpy as if it's saturated liquid, H of F, and it's going to go out at a temperature, and just like for our adiabatic saturation temperature, it goes out at the exit temperature T2. Okay, so if hot humid air comes in, cooler air goes out, the liquid goes out at the same cool air temperature going out. That makes sense. Then we also have the mass flow rate of the dry air going out times the enthalpy of the dry air at 2. It's a lower temperature, so lower enthalpy. And also the mass flow rate of the vapor going out. Now that's lower, right? The mass flow rates of the vapor going out is lower than the vapor coming in, H of G2. Now we can rewrite this equation so it's a little more readable. What we're interested in is this rate of heat transfer. And if you look at the units, it's kilojoules per kilogram of dry air. So it's Q dot over M dot dA. That's really what we're looking to calculate. So it's rate of heat transfer per rate of dry air flow through the duct and across the coil. So this, we just have to do a little bookkeeping to rearrange this. And what we're going to get is an enthalpy of dry air. Let me put it like this. 1 minus, the subscripts always are a challenge. Dry air 1 minus enthalpy dry air 2. So it's a change in enthalpy of the dry air. Okay. Then we're going to have the humidity ratio 1 Hg1 minus humidity ratio 2 Hg2 minus, I didn't leave enough room, this m dot liquid divided by m dot dry air, and we already said m dot liquid divided by m dot dry air is omega 1 minus omega 2 times HF2. And often we rewrite this change in the enthalpy of the dry air to be simply the specific heat of the dry air times T1 minus T2. All right, so at this point, we know we can get a value for the specific heat of air. 1.005 is a typical number used, kilojoules per kilogram Kelvin. We had already calculated our humidity ratios, omega 1 and omega 2. We have to get H of F and H of G. Okay, so our enthalpies for saturated vapor at the inlet temperature of 48 is 25, 80 something. And then look it up here and then look it up there. And so we can make that computation. Let me do this. I'm going to jump to an Excel sheet because I think I can play with the numbers and change them around. So I'm going to jump to an Excel sheet right now. And what I just noticed in my Excel sheet was this number right here. I need to fix it. I don't know why in my Excel sheet I have 47, but I'm talking 48 in the problem. So let me just quickly turn this around and change that. Let's see if I can do this. Please, please work. Please work. All right. So that's 48, right?
Yes.
Okay, so now we're consistent. Let me introduce you. So an inlet column, temperature in degrees C, pressure in kilopascal, and then the relative humidity. And then what we did was we made a call to get the saturation pressure at that temperature. So in the previous slide, I wrote the wrong value. So this saturation pressure needs to be like 11 point whatever it was. Okay, so we're slightly off there. But let's jump over to the Excel. And then you just multiply the relative humidity times the saturation pressure to get the actual vapor pressure. I like to always do it in 2 steps. Subtract to find the actual dry air partial pressure, and then compute the humidity ratio. So it's 0.0213, somewhere in there, 0.0213, okay? And now, this is the enthalpy that's recommended to be used for the vapor coming in, H of G. And you can see how we look it up. It's the enthalpy, in this syntax, HV underscore T of water. So as a function of temperature, what is the saturated vapor's enthalpy? You could also do it this way, and notice these two numbers are slightly different. Here, what are we doing? We're saying, give me the enthalpy as a function of pressure and temperature for water, and the pressure is the partial pressure, and the temperature is 48. So it does give you a slightly different answer, okay? But not much. I mean, it's good to 3 digits, but not the 4. But we'll use H of G, and that's what's recommended through the textbook. Now, if you go out and say, okay, we're coming out at 15 degrees C at the outlet, and the pressure, humidity, we assume, and then we check, and it works out that it is saturated air. That's the saturation pressure. That's the actual vapor pressure. The partial pressure dry air is much larger. The humidity ratio is much smaller. So you can see that this is a larger number, this is a smaller number. And you notice that there's much less difference. Well, even then, this code had a little problem, because if I just fed it the vapor pressure, it was a little confused, so I had to feed it 0.99, or you could put 0.999, and then it doesn't like 0.999. I need to back it off a little bit, and there you go. So we get the same H of G. Yeah, that's what happens. You wrung out some moisture. So as it was cooled, it hit a point where it hit the dew point temperature, and then it was 100% relative humidity. It started to saturate. It stayed 100% relative humidity and continued to saturate or dew out. You know, it stayed saturated air. Here's the enthalpy of the liquid at that exit temperature of 15 degrees C. So I'm going to come up here and say, here's the answer for the mass flow rate of liquid divided by the mass flow rate of the dry air. It was the difference in the two omegas. True? So there you go. And so it's a positive number, and we're getting some condensate. I also put in a specific heat for the air. Also, if you wanted to, you could try to approximate specific heat for water vapor. It's just the changes in H of G divided by the change in T, and you find that that average specific heat for water vapor is 80% greater than that for dry air. It's larger. So for every kilogram of water vapor that just changes temperature 1 degree C, there's more heat required to be removed or added if you're cooling or heating it. Now let's do the energy balance. So this is my way of writing C sub P times delta T. So it's how many kilojoules per kilogram of dry air due to just cooling the dry air. You need 33.1 something kilojoules per every kilogram of dry air just to cool the dry air. Then if you look at the equation and you sum it up this way, this is all the energy associated with the water. That's omega 1 Hg1 minus omega 2 Hg2 plus, and then the change in omegas times HF2. And it's 27. So when you sum them up, you need 60.66 kilojoules per kilogram of dry air flowing. And then if I look back, I say, well, 55% of it is cooling the dry air, and then 45% of it's associated with cooling the moisture, the water. And if you want, you can bust it out into two phrases. This is the same calculation. Look at this number right here. 60.66 is the same here, here, and here. It's just now trying to understand what are you doing in the cooling of the water. Okay, one way is to just cancel this. One way is to just take and separate out this part and that part in here. So these two, right here and right here, sum up to the other. And this is just saying, if I had all of the inlet vapor and I cooled it and not condensed it, I know it's impossible to cool all the vapor, but if you did, you would require, going from 48 to 15 degrees C, it would require 1.26 kilojoules, not much. And then if I just took and condensed at the 15 degrees C, how much needs to be coming out as liquid? Just going Hg2 minus Hf2, that's 26. So 43% is associated with condensing that little bit of water. And if you look at it a slightly different way, you just take omega 2, this is still algebraically correct, omega 2 times delta H G's, okay? Then you only really have 1% of the cooling for the vapor that never will condense. But the other part, the 44.3%, it cools it and condenses it. So it's going all the way from vapor at 48 to liquid at 15. And so we see that a bunch of that energy is associated with condensing. There's a couple things you can do with this. This 15 degrees C, it's below the dew point temperature of this inlet air. What you could do is say, just click right here. If I start changing this outlet temperature, it'll change how much liquid is produced. If I just cooled it to the point of being humid air without condensing any liquid, I could now calculate that temperature. So I'm going to do a what-if analysis with Goldseek and set that value to 0, meaning I don't want any liquid coming out. And by changing this cell, saying it's going to come out at a temperature which really is going to be the dew point temperature for the inlet air. And so the dew point temperature is about 25.7. Now, whenever you use Goldseek, it's a little tricky because it thinks that number is really, really small. But if you multiply that number by 1,000, you can do a what-if analysis on that number to say drive that number to 0, because it doesn't know relative numbers. It's 1, 0.1 is pretty small. By changing this number, 25.7, it won't change much, but let's see how much it changes. 25.9. So you really drove it to 0. So that's the dew point temperature, 25.9. And notice, there's no energy associated with condensing. It's almost all associated with cooling the dry air. 96% of the energy cooling is just to cool the dry air. It's a lot cheaper to air condition buildings and homes in West Texas, where you don't have a lot of humidity issues, versus the Houston, New Orleans, etc., where you have a lot of moisture. It takes a lot more energy to cool it. So there you go. Let's put this back to 15 degrees C. There's one other thing I did in this Excel spreadsheet that I'll show you. And you can get a number for the enthalpy of the mixture. This equation right here is just saying I'll take a specific heat, multiply it by the temperature, and that's a measure of the enthalpy of the dry air. And then we'll add to it the humidity ratio, omega, times the enthalpy of the vapor. And now I have an enthalpy of the mixture. By itself, it's not good, but if I get another enthalpy of the mixture, this one, similarly calculated, whoops. Let's just show you that similar equation. C sub P times T, omega times H of G. Then if I just take the difference in these two, I didn't really do that, but I can do it over here, is equal to the H on the inlet minus the H on the outlet. It's actually very close to our delta H. What's missing in this formula is H of F, is our H of F. That's what's missing, okay? Because if you look at this formula, it doesn't use H of F, does it? But often the enthalpy content of the saturated liquid is small. So you just have this shortcut, H of the mixture. So if we go back, we can wrap up that problem. What is it? You know what? I'm not going to wrap it up because I see that all my numbers were thrown off. Okay, so you'll have to just compare, fix it. But let's move now to what is the psychrometric chart. I often don't want to introduce the psychrometric chart to students too early, because then they just want to use the chart to solve all the problems. This chart has a lot of information. First of all, remember that we have knowledge of two humidities. We have relative humidity and humidity ratio. This one gets more talk out in the literature, out in the newscast, etc. And probably you're more familiar coming into this class. But the engineers really like humidity ratio. We do a lot of calculations based on humidity ratio. And then we have some temperatures. We have the dry bulb temperature. We have the wet bulb temperature. We have the dew point temperature. So 2 humidities, 3 temperatures. That's a lot of information already to try and put on one plot. But then we also have, and we didn't talk about it too much, the specific volume. This would be how many meters cubed per kilogram of dry air. If you're trying to size a duct, you'll need to know how many CFM or cubic feet per minute, or how many cubic meters per minute of flow go through the. So it's a volumetric type of calculation. So often we need that specific volume as well. So 2 humidities, 3 temperatures, specific volume. It's a lot of information for one chart, but lay it out simply. The chart starts with the x-axis where you have the temperature of the dry bulb. That is your most common temperature, dry bulb temperature. And then on the y-axis, but don't plot it on the left, go ahead and plot it on the right and it'll be apparent why. They plot the favorite humidity, the humidity ratio. Okay? And so if I'm at a particular temperature right here and the humidity ratio is 0, it is dry air. So all along right in here is all the conditions known as dry air. But as you start to add some moisture, omega goes up from 0, you get more and more moisture. But you know that cold air, this is cold air down here at a low dry bulb temperature, and hot air, they can hold different amounts of moisture. The hot air can hold a lot of moisture. The cold air can only hold a little moisture. And so there's a sequence of states that go like this, and that's saturated air. So you go from dry air to saturated air, and everywhere in between is moist air. And so dry air had a relative humidity, phi, of 0%. Saturated air has a relative humidity of 100%. So it's put on lines now of constant relative humidity. The line of 90% relative humidity will look kind of like this. And then 80%, 50%, all the way down 30%, they'll fan out like that. So those are lines of constant relative humidity. So on this plot, we already have talked about 2 humidities and 1 temperature. Now, what happens if somebody says I have cold air that is really, really humid? This state is impossible in equilibrium. It would basically be a fog. The water droplets would interfere with visibility and you would have a fog. That's what you would have, okay? So, but there is no moist air out in these conditions. This underneath that saturation line, 100%, that's where you have moist air. Now the other temperatures are a little tricky. Pick a point, just pick a temperature, and let's say it's right here, okay? Now, how do I find the dew point temperature for this condition right here? Well, conceptually what we did was we cooled it and cooled it and cooled it at constant humidity ratio, And as we cooled it, the dry bulb temperature is dropping until it becomes saturated air. And so on a psychrometric chart, that's how you find the dew point temperature.
Because at saturated air, all three temperatures are equal.
That's exactly right. And if it was at this condition right here, not this one, you would say the dew point and the dry bulb and the wet bulb temperature, all three are at the same. All three are at the same along that line. But to find a line of a constant wet bulb, I'll just tell you, they're sloped like this. So if I was at this condition right here, I could say, give me my dry bulb. Okay, it's right there. Give me my wet bulb. It would be this temperature. It's a line of constant temperature right in here. And usually there's a number on it, or it comes up and there's an index up here and you can read it in there. Next slide has a psychrometric chart to it. But the lines of constant wet bulb are sloped like that. And then you would read off the dew point by marching over horizontally until it's saturated air, dropping down and reading the dew point temperature. Now up in here, I forgot to mention also, there's enthalpy of the mixture. Enthalpy of the mixture is like this, and they kind of project down the lines, and they're, for this class, they are essentially the same slope as the wet bulb. They're coincident. Now they're slightly off in a good psychrometric chart, but we only have 1 or 2 days of the psychrometric chart and we're done. So these are lines of constant enthalpy. Then that's the mixture enthalpy. That's the enthalpy of C sub P times the temperature plus omega times H of G.
And that's the lines that are on the chart.
Yeah. So here you can get one of those charts right here. Let me not take off the top one because I got something written on it. There you go. And this is now the chart. It's a little overwhelming, but hopefully we broke it down. What's on the x-axis? That's the first one. It's the dry bulb temperature. It's in degrees C. What's on the y-axis, but don't look to the left, look to the right for the y-axis, and it's humidity ratio in kilograms of water per kilogram of dry air. And then find that line of 100% relative humidity for saturated air. And it goes just like that, right? Coming all the way down. And then find lines of other constant relative humidity. Maybe you pick one that is 50%. Here's a 50% relative humidity line. And it goes like that. Notice cold air cannot hold a lot of moisture. Warm air, hot air can hold a ton. It can hold a lot of moisture. So 5-degree increase in temperature from here to here really greatly increases how much moisture, the air can hold, how much omega can go up. Okay. And then the lines of constant enthalpy, here's their specific enthalpy, so 40, 50, 60, and they kind of get you the slope going and you project it off and down. All right? So if you use it, you have to use a ruler. Straight edge, that's right. And then also they put these lines in here. Let's look at this one that hits at 20. It really is not a line. This line right here is not a line of constant enthalpy, although it's the same slope and everything. It's a line of constant wet bulb temperature, which is 20 degrees wet bulb.
Okay.
So this line right here takes you a while to figure out what that is. That line right there, because it's nice and thick, and this line is nice and thick. This one, oh, it's 10 degrees wet bulb. This one's 20 degrees wet bulb. This one was 15. 15 degrees wet bulb. And then you can see, oh, that's 11, this one's 10, 12, 13, 14, 15. And so you get used to reading it, of lines of constant wet bulb. So let's do this. Let's go back to our problem that we had. It was 48 degrees, true? Find 48 degrees and 30% relative humidity and put a dot for that inlet state. So 45 is there, 6, 7, 8. So that's a line of 48 going up. And we want to go up to 30% relative humidity. Is that what it was?
Yes.
And so it goes right to there. Boom. Okay. At that state, can you read off omega? Can we come over and read off omega? It's a little bit above 0.021, true?
Yep.
And now, if you allow me, I'm going to click back to the Excel sheet, and we calculated that it was 0.0213. You can't get more digits than that on a chart, right? Mm-hmm. So 0.0213. So 0.0213. It looks very reasonable. Now, the other one, since we're at that state, we never did do the, we did do the dew point. Remember we came across, we said, hey, find that dew point temperature. What did we say the dew point temperature was? Didn't we say it was around 25 point something? 25.7. And you know what? It looks pretty good, doesn't it? Doesn't that look pretty good to 25.7? So the dew point, 25.7. Now, we never did the wet bulb, but this is a line of 30. That's a line of 31. So the wet bulb looks around 30.7, 30.8. Wet bulb temperature. So for each state, we should be able to get the omega, the phi, the temperature dry bulb, the temperature dew point, the temperature wet bulb, and you can also get enthalpy of the mixture.
Okay, so the wet bulb is right between where the omega and the dry bulb temperature meets.
Yeah, it's you look like you have to interpolate this way between this line and that line.
Okay.
This line's 30, that line's 31, and it looks like it's around 30.8. So for the wet bulb, 30.8. And now the other one, if you want, you can extrapolate this back and pick off a mixture enthalpy. And I would say it's around 104. The mixture enthalpy is maybe 103, 104 kilojoules per kilogram. Let's jump back to the Excel code to see what it came in at. 103 point something. So you can confirm these numbers. Let me jump over back to the psychrometric chart. Okay. Now, what happened was you started to cool it. And when it first came across the coil, it cooled a little bit, cooled a little bit, cooled a little bit, cooled a little bit, cooled a little bit until it, as it's flowing across the coil, deeper across the coil, it finally reached a temperature about 25.7, and it still wanted to be cooled all the way to 15. It starts dewing out now. It starts dewing out, dew, till you get to, here's 15 degrees. And this is 100% relative humidity. That's saturated, true? So it goes all the way to this point. So that's the path. Like that. And at that point, the three temperatures are trivial, aren't they?
Yeah,
but
they're all the same.
But you could read across and get omega. And so it looks like omega is around 0.0105. And let's jump back to the Excel and take a look. Omega 1.0106.
That's pretty.
Yeah, it's pretty good. And so we'll jump back over here. And then also, whoops, you should be able to read off the enthalpy. What's the mixture enthalpy look like? Oh, I'd say around 42. 42.
42.
And if we jump back to the Excel code and take a look, it's mixture enthalpy. Whoops, I went to the wrong Excel code. I should close this other file. It's 42.01.
In the ballpark.
Or even do the calculations in the first place. Once you get good at the chart, people don't want to let go of it. It's like, hey, this is so easy. All those tedious calculations.
Oh, yeah.
So students really love it. You have to pull them off and say, no, no, no. Do not use the psychometric chart for this problem.
Oh, no.
Now, the way that instructors can easily do that is what they'll do is they'll say something like, this chart right here is good at what pressure? Atmospheric pressure. They change the pressure to make up some ridiculous pressure. Oh, it's 0.8 ATM. That shifts everything. The chart, if you use it as 1 ATM, will be close, but it won't be exact. So there's the rub. That's how the instructor like myself would force a student to say, hey, no, you can't use the chart. That's only good for 1 ATM. Yeah. Okay, so the enthalpies look great. And if you wanted to, the specific volumes are right here. This line, you see how they're sloped? They're sloped that way. And so they're very steep. So the specific volume and this current, 0.85, and then this is 0.90. And you just have to read the specific volume if you wanted to. I didn't use it, so. All right. And then you could even estimate, some people will do it, they'll look at this value of enthalpy and they'll say, look, you did all of this basically to just cool the air without condensing anything. This is when you were cooling and condensing. And then you can see, oh yeah, that's a lot of energy. But you're still cooling the dry air there too. So, but if you wanted a real good breakdown, you could look at the code. And that's what we did here. We're looking at 55% just to cool the air. And the rest, 45%, is due to condensing and cooling the water vapor. Well, that's it for today. Eli, thank you for coming.
Thank you.
I'm going to shut this down.